Welcome to Wings of Aero, Advanced Education and Research Organization. Hi friends, today we will see few of the solved question and answer of propulsion solution which has been asked in GATE 2019. First question. For the complete combustion of 1 mole of ethanol, C2H5OH, the required amount of moles of oxygen is. Here we know when the ethanol is getting mixed with the oxygen, so which will give carbon dioxide and water. So we can frame the equation like ethanol plus oxygen, and which is giving a product of carbon dioxide and water, and we need to balance this equation. When we balance this equation, we get as C2H5OH plus 3O2, which gives 2 moles of carbon dioxide and 3 moles of water. So from here we can understand the right answer, the required amount of moles of oxygen is 3. So right answer is 3. Next question. While flying at the Mach number 2 at 11 km altitude and producing the same amount of thrust, what is the correct order from the lowest thrust specific fuel consumption to the highest TSFC? We have 4 options: turbofan, ramjet, turbojet. Then second option, turbofan, turbojet, ramjet. The third one, ramjet, turbojet, turbofan, and D is turbojet, turbofan and ramjet. We will see the solutions. Remember these parameters. We know that here specific impulse are inversely proportional with the SFC. So from here we can pick up that turbojet, ramjet and scramjet are gradually decreasing the SFC. So it will be inverse of that, that is scramjet has the highest SFC compare with the ramjet and compare with the turbojet. So from here we can come to a conclusion that option B is a right, from where the SFC will be less in turbofan in compare with the turbojet and in comparison to turbojet to the ramjet. So answer B is a right option. Next question. The propulsive efficiency of a ramjet engine is lower than that of low bypass ratio fan engine operating under the same conditions and producing the same thrust. Preliminary, because the ramjet engine, there are 4 options, has larger kinetic energy lost in the exhaust jet, B has a lower thrust power, C is self-starting, D has a higher thrust to weight ratio. Before that, we'll see what is meant by propulsive efficiency. It is defines the ratio of useful thrust power output to the propulsive energy, that is a kinetic energy. So from here we can understand if the kinetic energy is high, then the propulsive efficiency will be less. So from here also we can see this formula and we can pick that the option A, that is having the high kinetic energy which produce a less propulsive efficiency. So option A is the right option. Next comes, for a single stage subsonic compressor, which of the following statements about the highest possible compressor ratios is correct? There are 4 options. Option A, compressor ratio of an axial compressor is greater than the centrifugal one. B is axial compressor is less than the centrifugal compressor. And option C, centrifugal compressor is equal to the axial compressor. And D, that CPR of any value can be attained either with an axial or a centrifugal. Now before that we will see a solution how this axial compressor and centrifugal compressor are varies with each other. So you can see the axial compressors are used for a large engine, whereas the centrifugal compressor are used for the small engine. Whereas axial compressor have the highest mass flow rate more than 100 kg per second, and whereas the centrifugal compressor having very less mass flow rate, about 15 kg per second. Next comes axial compressor having highest efficiency, 93 to 94 percentage approximately, and whereas the centrifugal compressor having low efficiency in compare with axial compressor, about 86 to 88 percentage. And next comes, here comes the real answer. You can find out when we are using the pressure ratios per stage, which is as low as 1.5, and whereas a centrifugal compressor having the high as 5 to 7 of the pressure ratio up as per stage. So from here we can pick the right answer, that centrifugal compressor is greater than the axial one. So our right answer is option B. Here comes another question of an axial compressor. Here the figure shows the velocity triangle for an axial compressor stage, and from here we need to find the specific work input to the compressor stage is in kilojoule per kg. Approximately round off to 2 decimal places. Here is the figure given. So in this, first we'll recall the formula for the specific work input to the compressor stage. The formula is W equals to U into CT2 minus CT1, that is tangential velocity of 2 to the 1 stage. Now these are the data has been given, and which is not given we have to find out. Now as per the given figure we can obtain what is C2 from the given figure. When we draw a straight line from here, and this from here to here, this has been given as 40, so total is 100, so we can find the CT2 is 60 meter per second. Now similarly we can find for the first triangle, when we draw a perpendicular line from here, we need to find this. Now how we can need to find this CT1? This is forming one triangle. We know this angle is 30 degree, we know this 60, the vertical, the axial velocity we know CZ is 60 meter per second. Now using this formula we can write the tan 30 equals to CT1 by CZ. From here we substitute the values. From here we can find what is CT1 equal to 60 into tan 30, and we get the value 34.64 meter per second. And we know the value of U, that is blade speed value, is around 100, and CT value we have already found out here 60, and CT1 we just found out 34.64. We need to just substitute the values, and we get the value in kilojoule per kg is 2.454. Here we need that the rough answer, which is answer ranges from 2.5 to 2.60, which is within the limit. Next question. The combustion products of a gas turbine engine can be assumed to be a calorifically perfect gas with gamma equals to 1.2. The pressure ratios across the turbine stage is 0.14. The measured turbine inlet and the exit stagnation temperature are 1200 Kelvin and 900 Kelvin respectively. The total turbine efficiency is we need to find and round off to nearest integers. Now let's see the solution. So here are the given data, gamma equals to 1.2, and they have given the pressure ratios as P4 by P3 as per the Brayton cycle, and T3 is the turbine inlet pressures, which is given 1200 Kelvin, and T4 is the exit temperature of the turbine, which is 900 Kelvin. And the formula which we can know that turbine efficiency formula is actual by isentropic. Based on the Brayton cycle, we can write T3 minus T4 by T3 minus T4 prime, which is isentropic, or we can also call as ideal. Now we need to substitute the values. We can see in the figure, and now from here we have taken the T3 common, and we can write 1 minus T4 prime by T3. Now, as per the isentropic relations, we can write that T4 prime by T3 equals to T4 by T3, which is given in our data. After substituting the values, we get as T4 prime by T3 equals to 0.72. Now this value we are going to substitute in the given formula, that is, and we can find the efficiency about 89%, and as per the given data the answer will be ranging from 88 to 90%, and which is within the reasonable zone. Next question. 1 kg of diatomic gas is heated and its temperature increases from 100 Kelvin to 600 Kelvin. The energy added at constant pressure during this process is 500 kilojoule. The specific heat at the constant volume of the gas is kilojoule per kg Kelvin. We need to find with a round off of 2 decimal places. Now let's check the solution. As per the given data, the gamma is 1.4, T1 value is 100 Kelvin and T2 is 600 Kelvin, and the Q is given as 500 kilojoule. And here when we are considering at constant pressure, we can consider the P1 equals to P2. Now as per the formula in first law of thermodynamics, at constant pressure we can get this formula, that is Cp equals to Q by m dot of delta T. Delta T is a change in temperature between these two zones. When we substitute those values, we get a Cp value is 1 kilojoule per kg Kelvin. And now recalling this calorific value, calorific perfect gas, and we can get that Cp minus Cv equals to R. We know the respective values. R is 0.287 and Cp we got as 1, and when we substitute the value we get as Cv, that is constant specific heat at constant volume, is 0.714, and round off to 2 decimal places we can write Cv equals to 0.71 kilojoule per kg Kelvin, and the answer can be ranges from 0.7 to 0.72. Next question. In a turbojet engine, the compressor outlet temperature increases with a decreasing efficiency of a compressor. If the turbine inlet remains constant with a decrease in the efficiency of a compressor, the thrust specific fuel consumption of the engine, what will happen with the 4 options? Decrease as the heat input is low, remains unchanged. C. Then increases as the compressor need more work input from the turbine. D. Decreases as the thrust produces high. Let's check the solution. Here are the formula for the efficiency of a compressor, that is isentropic by actual. So recalling the Brayton cycle, we can frame that eta C equals to T2 prime minus T1 by T2 minus T1. That means which is the isentropic work done by the real work done. Now here the question is but the turbine inlet remains constant but with a decrease in efficiency, but how it will affect the SFC? Now thing is, now this parameter is increasing. Due to increase in this parameter, the total difference will also increase. So if this parameter increases, then the efficiency will obviously go down. That means here, since there is an increase of this, there is an increase in this parameter work done. So if there is an increase of this work done, and there will be decrease of this parameter because this parameter is constant. So if this is decreases, obviously the SFC will increase. So we can see the right option. So it is very much clear that SFC of an engine which increases as a result that compressor need more work input from the turbine. So right answer is the option C.